Welcome back, everyone, to the second session of the first ever Machine Learning for Forensic Practitioners Summer 2022 short course sponsored by NIST. Back for round two, your speaker today again is Dr. Heike Hofmann. Dr. Hofmann earned her PhD in Augsburg, Germany, and since 2002, she's worked as a faculty member at Iowa State University, earning responsibilities and titles such as professor in the Department of Statistics, professor in charge of the data science program, the Kingland Faculty Fellow, American Statistical Association Fellow, and the AFTI Technical Advisor. In her role at CSAFE doing research, she's used a significant amount of machine learning, and we'll share some of that with you today. Dr. Hofmann, you are cleared for takeoff.
Thanks, Anthony. Thank you for the nice introduction as ever. Welcome, everybody, back to round two of this short course. I want to just give a quick shout out to our sponsors. So this work's partially funded by CSAFE through NIST. And you are all aware of all of our amazing collaborators. This is still joint work with Alicia and Jeff, who are hopefully hanging out as panelists and fielding some of the questions that come up during the course. Afterwards, I'm happy to give some feedback or answer questions like last time. So just to get back to our big picture, part 1, 2, 3. Last time we were talking about just bigger picture questions. So what is machine learning? We looked a lot into classifiers and talked a lot about how to measure and evaluate performance. What we're going to do today is focus on tree and algorithms and loss functions, in particular of trees and random forests. So just as a quick review, we were looking at the MNIST database. Just as a reminder, that database consists of a lot of little images, so 28 by 28 pixels. So for each of these little digits, we have a very small little picture of just 28 by 28 values that are somewhere in the range from all white to all black to show us those little digits that are on the screen. So we've got 60,000 images for our training set and another 10,000 images for the test. So we have labeled data, and we talked about last time how we're using labeled data to split into a training set, a validation set if we need to work on internal parameters, fine-tuning of those internal parameters, and then a test set that is a holdout set that is not used in any which way for training or fine-tuning parameters. We were also talking about different performance evaluations. For today, we're just going to look at overall accuracy and accuracy of individual classes. So we're not going to go into a lot of confusing details about sensitivity, recall, precision, or what else were there? There were a lot. We were also talking about logistic regressions, and we're going to come back to logistic regression, but only in the sense that we're going to compare our trees and random forests to the initial logistic regression model. Okay, so one of the questions that we were asking last time was, is it a 7? So I just picked the 7 here because when you have a look at all of this, the 7s look really interesting. And I know from running the full random forest on all 10 different digits, the random forest tends to have difficulties with identifying sevens and telling them apart from nines and ones, and sometimes fours. So we were running this random forest, and we had a training, or in this case, it's called out of bag estimate of the error of about 1.08%. Running this random forest model on our test set, our holdout set that has not seen or has not contributed to the random forest, we see that we have a similar test error, an overall error of 1.03%, so even slightly better than the training set. And that compares directly to what we saw in the logistic regression of just under 5% error of the logistic regression on the training set of on the test set of trying to distinguish a 7 from anything but a 7. So it's definitely worthwhile to look into these random forests. And before we look into the random forests, we'll have a look at a tree. So a random forest, like the name suggests, is made up of a multitude of trees. So we'll have a look at trees first. Let me get back to that idea. What we also talked about were those performance measures. So one performance measure that is suitable for any kind of machine learning model is drawing the receiver operator characteristic curve. So these are the curves where we're drawing the false positive rate at a certain threshold against the corresponding true positive rate for the same threshold. So we get a set of points and we connect those points in these lines. So here you see lines for the logistic regression and a line for the random forest score. And you can see that the random forest score shoots up from 0 faster than the orange curve. So blue curve is higher than the orange curve from anywhere from 0 to 1. That indicates to us that the random forest at every single threshold dominates, is better than the logistic regression at any one of these thresholds. You can also see this hatched line along the diagonal. That hatched line would be us just flipping a coin. We see an image, or we don't see an image. We flip a coin and we guess with a 1 in 10 chance that an image is a 7. That will give us a process that will land on this hatched line. So that is guess what happens when we guess. As long as our method is better than guessing, we will be above that diagonal, and best case scenario, we fill out every space along the 0 line, and then follow vertically and then horizontally the line with the 1. So you can see that the random forest score is very, very close to being perfect. And there's just a tiny bit of the curve where the curve is turning at the very top left edge of the image of that plot, where we don't capture, where we could where we could improve things. But there's not much room left for improvement using the random forest. With the logistic curve, you can see that there's quite a bit more room left. So another measure that is oftentimes used is called AUC. That's the area under the ROC curve. So area under the curve, AUC, all these fun 3-letter abbreviations. So AUC is the area that we see under the orange curve or under the blue curve. It's a value between 0 and 1. So this whole area is one unit wide and 1 unit high. So best case scenario, the AUC captures this whole area and we get a 1 back. That means that the corresponding model has perfect performance. If we have an AUC of 0, that's actually perfect non-performance. So there is, when we guess, when we are in the worse than guessing area, there's actually skill in being so bad at guessing that you need to actually work at that. So a 0 is very unlikely. It would be a perfect guesser, a perfect guesser that always gets it wrong. So we could easily fix that and make it a perfect guesser. So perfect guesser and perfect misguesser is almost the same thing. So guessing is actually a value of 0.5. So here I'm just showing the area sketched in of what the AUC shows. So guessing would be the line, the diagonal. And if you think about this triangle, remember 8th grade, maybe 7th or 9th grade arithmetic, the area of a triangle is 1/2 the base times the height. So 1/2 times 1 times 1 is 1/2. So that's the area under the curve of that diagonal. There's software that evaluates the area under the curve for the logistic regression ROC curve and the random forest ROC curve. And you can see that they're close to 1, indicating that they're very good at what they're doing. Logistic regression has a AUC of 0.959. Random forest is at 0.998. So there's only 2% of this whole square missing at the top left of the overall area where we could improve the performance. So AUC is another measure that is sometimes reported when people are dealing with machine learning models. So the closer to 1, the better. So what we want to do is we want to grow statistical trees now and then look at random forests and then talk a little bit about feature extraction. So let's get started with trees. So trees are quite old for machine learning tools. So they got started by Leo Breiman in his CART algorithm. So classification and regression trees is what stands behind that acronym, CART, CART. We're just going to look at classification trees. Regression trees have a different kind of dependent variable. We are mostly interested in labeling outcomes. So that's why that's called the classification. So that's why we're just going to have a look at classification trees here. So our dependent variable is ground truth. So we've got the labeled observations. And the basic idea is we're going through our data, our features, our variables, all of that's the same thing, remember? And what we're doing is we're trying to find subsets of the data that where we don't have as much mixing of the labels when we split according to those subsets. So we're going to use binary split. So we're just going to look at one group versus another group, and we're trying to put those splits into the data in a way that we purify the data so that observations that have the same label can hang out together in their own subset and not mix with the other labels in the other subset. So more formally, trees are grown as sequences of binary splits. And trees start from a root. The way that statistical trees grow, they're actually hanging trees. So they start from a root at the top. And then at each node, so we call these internal branches, or where things branch off, we call those nodes, sorry. So the root is a node, and in each of these nodes, we're asking questions of the form, looking at variable x4, is the value less than 3.7? Yes, then we go this way. If it's larger than 3.7, then we go the other way. So if yes, go left. If no, go right. And that way, so we keep doing that until we've got final nodes that are about as pure as possible, or until we just stop. So we use our training data to grow those trees. And once we have a tree and we get a new item, the way that we apply this model is we just look at the features of that new item and we pass the feature down along the tree until it reaches a final node. And that final node determines what we would classify this new observation to be. So let me just give you an example here. So this is an example that we will see later. This is an example that we actually partially use in a random forest that distinguishes striation marks on bullet lands to figure out whether the bullet was fired from the same or a different barrel. So we've got a couple of different features that we're observing here. So here we're just looking at the number of matching stria. And then CCF is cross correlation. We'll come back to that. Right now, it's just a variable in our data set. So, and you can see how this tree is made up of a couple of decisions. So we've got internal nodes. Those are the wide rectangular nodes. That's where we make decisions. And then we've got the colored nodes. Those are terminal nodes, and they have a label. So you can see that we've got 3 outcomes to go with an outcome of different barrel, 3 outcomes with the same barrel that doesn't necessarily have to be the same. It just happens to be that way. But the way that we're then using that, so assume that we've got a new comparison, and in that new comparison, we have 10 matching stria, and the cross correlation between the signatures is 0.65. So the way that we use this tree now is we always check from the top. So we have a look at, is the number of matches less than 14? In this case, it's 10. So we would say yes and move down to the next decision that we need to make. So cross correlation, is the cross correlation less than 0.75? In our case, this is 0.765. So when we ask this question, we say yes, and then the process starts to go through. So we're multiply checking the number of matches and the cross correlation again, and we finally end up in this blue terminal node that says same barrel. So in this case, our tree would say this new comparison is so the model says that the two signatures that we're looking at here come from the same barrel. So that's how we use a tree in practice. So it's relatively easy to use, and it might be relatively easy to explain to jurors or just colleagues. What we're looking at: number of matches, cross correlation function, and this outcome. Obviously, in order to get to the point where we say how many matching stria there are and what the cross correlation is of a comparison, there's some work that needs to go in there in order to get to those quantifications. But this would be a quantification of a comparison of two engraved land areas that allows us to say whether this is from a same barrel or a different barrel. And please don't take this model and apply it. There's much better models that we have, not just this tree. This tree is not bad, but it needs a lot of fine tuning. So please don't use it in practice. This is a toy example. But it's relative. So I just want to show how we use a tree. And you can see that there's a couple of decisions that we need to make. And it's relatively easy to see how it comes to a conclusion. So let's back up a little bit. So like I said, a tree is grown from the top. And we start with the full data set. And now at the top, we want to find a split along a variable, so one of our features, that creates the two purest subsets. So two purest nodes that we can with just using just one variable. So purity is measured as the Genie coefficient. So Genie coefficients go back to Corrado Genie, back to 1912. And he was actually an economist and sociologist. So the Genie coefficient is also used in a lot of other fields, and usually, so our society tends to increase diversity rather than increasing purity. So the Genie coefficient is really a measure of mixture. So the higher the Genie coefficient is, the more mixing do we see. And in a tree, we're actually going against that. So instead of going in favor of mixing, we're going in favor of non-mixing. So we're trying to sort. So let's assume that we've got a tree with K labels, and I'm just putting the formula out here for K labels. It's not that different for just two. So let's just assume we have two labels. We have maybe same and different, or yes and no, or 7 and not 7. So in each node, we have a number of observations that go with one class. We've got a number of observations that go with the other class, we get the ratios of those. So that's the PI. So this PI is equal to the fraction of NI over the sum of all the NIs or NJs. That's just a fancy way of saying that we're getting the ratio. So let's say we've got about 10,000 sevens in our node and 50,000 things that are not sevens. So that would give us a 1 in 6 chance for a 7. So P for 7 would be 1 over 6. P for not 7 would be 5 over 6. And then the Genie index is calculated as 1 minus the square of the sum of all those squared proportions. So in the case, now I need to write this down so I'm not talking about any nonsense. So in the case of the 7 versus non-7, we said 7 has a P value of 1 over 6 and non-7 has a corresponding value of 5 over 6. So the Genie index would come out as 1 minus 1 over 6 squared minus 5 over 6 squared. So we square both the 5 and the 6. So somebody can do the math. 1 minus 26 over 36, however that is. The Genie index is anywhere between 0 and 0.5. 0 means that, so here we go. Yes. So if we just have two classes, it's a little bit easier. So we just have 1 minus P squared plus the other one to the square. So whenever P is 0 or 1, this Genie index is going to be 0. That's where we have perfect purity. And we have the least amount of purity when the value for P is half. So that's when we are in a node where we have 1/2 of one kind, 1/2 of the other kind. That's where we have perfect diversity, means really terrible purity. So we don't want to be in the middle part. We want to be somewhere on either end. So either one class or the other class. So the lower the Genie value, the better the split and the better the node. So I know that this formula looks really intimidating. So let's put that into an application. This is a really fun little data set about banknotes, genuine and counterfeit banknotes that's captured in the label status. So status has genuine or counterfeit. And then for each banknote, there are measurements for each node. So the length of the bill across, then the left edge, the right edge. So that's all in millimeters. So that they are from Switzerland. So that's why in millimeters. So 1/10 of an inch, right edge, the bottom margin width, the top margin width, and then the diagonal from one side, so bottom left to top right of a banknote. So when let's just have a look at these banknotes. So there's 100 counterfeits and 100 genuine banknotes that were measured. I'm not 100% certain that Ridwell and Fleury ever were involved in some banknotes, counterfeit or not, but the data set dates back to them. So I would love to learn more about the data. I couldn't quite figure out whether it was genuine, whether the data is genuine or not. So I would very much like it for it to be genuine. But here is an overview. So we've got all 6 measurements, bottom through top. So bottom, top left through top, bottom right. That makes real sense. I hadn't picked up on that. I'm sorry about that. Strange ordering. It's just by, it's just alphabetical. So all of the banknotes are one little square according to, or no, a little rectangle that's colored according to whether they're counterfeit or genuine. And what we'd like to see in any one of these features is a good separation between counterfeit and genuine bills. And just looking at these things are called histograms. So just looking at these histograms, we see that diagonal has a very good separation. There's just 2 bills that are hanging out with the wrong group. But bottom has also a nice separation. It's not quite as good as diagonal. The other measures are not quite as good, just looking at these. So how would we use the Genie impurity measure to come up with a tree in this situation? Let's have a look at the variable bottom. So I'm just plotting each bill with just a little circle. So the circle and the location of the circle in this dot plot is according to the bottom margin in millimeters that we see from this particular bill. So overall we have 200 bills, so you can count those little points, but I assure you there's 100 blue dots and 100 orange dots. So we've got a 50-50 mixture, which means that overall our Genie impurity or purity, our Genie impurity measure is 0.5. So it's as bad as it possibly can be. We've got complete mix. So now what we want to do is we want to split at one of these levels of bottom. And we want to evaluate if we split, say, at 8, and we look at everything that's below 8, we see that there's just one orange value among a sea of blue values on the left-hand side. So we can calculate the purity measure for Genie for just that node. And then we look at everything above that split, so 8 and above, and you can see that there's now more orange than blue. So it's a little bit better in terms of separation, but there's still a lot of mixture in the node on the right-hand side. So that's exactly what this diagram in the middle is trying to tell us. So we've got 2 lines here. We've got this purple line with that shows the Genie index for the left node. If we assume that the left node means we're looking at values that are below the split, so observations below the split. So we start out perfectly. We have 3 blue, 4 blue values. If we split our our root node into anything that's below 7.3, as opposed to anything above that. So we start out perfectly with 0. And then as soon as we increase to 7.4, we have one wrong thing in there. So the Genie index jumps up, and then it decreases slowly because we're just adding blue ones, and it still decreases until we're at 7.9. Once we hit 8, there's 3 more orange ones coming in. So our Genie value increases again on the left node. And we just keep going. So we're pretty level for a while, and then beyond about 9.5, our Genie index goes up more and more until we are at 0.5 at the end of, so the left node encompasses everything from the top root. So our Genie index is for each node is always going to start at 0 and go up to 0.5, or start at 0.5 and go down to 0. So as we increase the number of items that are included in our left node, the impurity goes up again. And similarly, as we decrease all of the values that are in the right node, so the right node starts with the full thing, so everything is included, and then successively we just kick out values into the left node. And you can see that as soon as we're at around 9.5 or so, we are at a quite low value, because mostly in the right node we have orange values, and that goes down to even 0 as we're at 10.4. So any values that are above 10.4 are all orange values. So they are all, I'm not sure, genuine or counterfeit. It doesn't really matter, but it's just one class. So that looks pretty good. So what we're doing overall is we're trying to find a balance between the left node and the right node. So overall, we want to get the Genie impurity down as much as possible for both nodes. So what we're doing is we're averaging between the green and the purple line in each split. And that's what you see as the black line. So the black line is the average of the Genie index between the blue line, the purple line and the green line in each split. So that line gets a minimum at 9.5. So that if we split our first node along bottom, and we check whether values of the bottom margin is less than 9.5, and we go left and compare to the bottom margin of B greater than 9.5. That leads to an average Genie impurity of 0.13. So we're going down from 0.5 to 0.13. So that's a reduction that this variable achieves of 0.368 on average. So in the average between the left node and the right node. So we do this kind of evaluation for all of our variables. So we've got bottom, diagonal, top, left, right, length. And what we're comparing is where can we find the best split that reduces the average Genie impurity the most. So here we're looking at top, and you can see that compared to the previous plot, the Genie So both the green line and the purple line stay pretty high before they go down or are up for a really long time. And also what looks good on the left-hand side, so all of this really long purple flat line at 0, when you have a look at how many values that actually encompasses, there's only, well, 6 values. So splitting off just 6 values from those 200 values is maybe not the best strategy if we're just shaving off little things. If we're shaving off like that, our tree is going to be very complex and very big. So we're trying to reduce, we're trying to only have nodes that have at least a minimum of usually 10% of the data. You can, we're trying not to use those splits that are at the very left or at the very right side. So usually we're aiming for splits that are somewhere in the middle. So if we're looking at the overall reduction, so this might be a place where we can achieve relatively good Genie impurity. Another option would be to split at 11.2. So the 9.9 split is just a little bit below the 11.2 split. And it results in a Genie impurity of 0.269. And you can tell that it's already almost twice as big as the previous variable. So top is not going to be the variable that we're going to choose to split for the split in our root. So when we're actually running the tree model on this data set, the final model is a very, very small model. We're just looking at diagonal. If the diagonal is less than 141, we say that this is a counterfeit. If it's larger than, if the diagonal is larger than 141, it's the genuine thing. So here in this model, we're done after just one split. Generally, once we've split once, we're moving into each one of those nodes and we just repeat the process. So manually, this sounds like a terrible way of processing things. So we definitely don't want to grow trees manually. That's way too much work. But the good thing is computers are really good at this and really fast. So tree models are a bit more computationally involved than logistic regressions, but the trees are very fast computationally. So even though it looks very involved. So the good thing is trees are really fast. So the question now is, if we keep moving into each node and splitting, when do we stop? So there's certain stopping criteria involved. So either we've achieved a Genie impurity of 0. So if it's a perfect split, we might just as well stop there. We also don't want to keep splitting if there's if we're below a minimal node size. Sometimes, so if we don't want to go below maybe 10% of the overall number of observations, we also might want to not deal with very complicated trees. So we could set a maximal tree depth. So here we just have one split, so it's a depth of 1. In the very first example, I think we had a maximum of 4 splits. So we can just set the number of splits, this tree depth, as a stopping criteria. So, oh yeah. So when we report these the results. You can see here we've got labels in the terminal node. So it says counterfeit and genuine. And this is also supported with two numbers each. So on the genuine side, there's a 0 and a 98. So 0 means that there is no counterfeit in this terminal node, and we've captured 98 genuine bills, and this makes overall 49% of the data. So overall we've got 200, so 98 are in this genuine in this terminal on the right hand side, so that's 49% of the whole data. So the percentage of the comparisons that or percentage of the bills, the overall bills is given in that percentage down there. So what we see on the left hand side in the left node, there are 102 bills in there, 100 counterfeits. So we find all of the counterfeits, but we're including 2 questionable bills in the counterfeits that are actually genuine bills. So that's 51% of the data. So we've got it nicely evenly split. So the advantages of tree is, like I said, trees can deal with large amounts of data, and that means both large in terms of the number of observations that we've got and large in terms of the number of variables. We've only looked here at yes, no, so binary dependent variables, but trees can just the same deal with multi-class classification. So it's not a problem to just give the tree all digits, so 0 through 9, and run the classification that way. I would like to think that trees are relatively easy to interpret. And what's also nice is that we can mix qualitative numbers, so qualitative features, qualitative and quantitative features. So quantitative numeric measures can be mixed with categorical evaluations, so qualitative evaluations of features. What's also nice that oftentimes trips up linear models is that nonlinear relationships between the dependent variable and each one of the features can be, the tree can deal with that. So those nonlinear relationships don't affect the performance negatively in any way. So what about the disadvantages? Essentially, the disadvantages of trees are their lack of stability. So if we've got, if we make a small change to the training data, that might change the split at which we split a variable, or it might affect even which variable is the best variable to pick. So it might result in structural changes of that tree. So it's going to be hard to explain to somebody why it has changed so dramatically when just a couple of training data were added or a couple of training observations were excluded from the training set. So trees are also have a tendency to overfit. So what that meant was they have a small error on the training set, but then really large errors on a test set. That usually happens when we have really complicated trees. So we want to avoid those really complicated trees by either not going that far down or not shaving off really small nodes with small numbers of observations. What that is called is pruning. So just like your hedge can be a little bit too complicated and you cut it back, we prune trees by snipping back the very the decisions that become too complicated, so we can prune trees back. But for that, we need to figure out where they overfit. At the same time, trees can also underfit small categories. So for example, when we only see something in, so let's say we're looking at fraud detection and we've got hundreds of thousands of bank transfers, and we are looking at fraudulent charges. Hopefully the number of fraudulent charges are very small compared to compared to regular activity, non-fraudulent charges. So a tree that will always say, oh, that's all right, is going to have a very small overall error, because by just saying everything's fine, it leverages the fact that there's not that many cases where something bad happens. So when we're training a data set like that, what we should try is to balance the training set. So rather than using all of the cases where there's, rather than using everything, we can pick, we can use all of the fraudulent cases and then pick from the non-fraudulent cases, important cases or cases that are close to being fraudulent, so that we can train the model to see the difference between what's fraudulent and what's not fraudulent. So we want to find balanced data as, we want to start with balanced data as much as possible. Okay, so here is, we're back to the example of, is it a 7? So here is a tree, and this tree is using the MNIST data, where true means it is a 7, false means it's not a 7. So you can see there's how many terminal nodes? About, I don't know, 15? Quite a few terminal nodes, a lot of internal nodes. And in each internal node, we have a decision like, look at feature 741. If that feature is less than 1, so essentially that means it's white. So if it's not white, so if that is a black spot, go to the left-hand side and have a look at right-hand side. Right-hand side, no. So if that is a black spot, go and have a look at the value that we see in spot number 406. And if that's also a black spot, then we're pretty certain that this is a 7, and there's 1,801 sevens in that terminal node, and 134 non-sevens. So that's where this particular tree stops. We can see that overall these about 2,000 observations that are captured by this terminal node make up about 3% of the overall data. So when we're having a look at overall where the mass of the data is, we'll find the node on the very left It's a light blue node, so it's false. So it's not a 7. And we can see in how we get to that 7. So we are looking at the features 741, 710, 744, 714, 746. So these are all pretty cryptic variable names. But whenever they are less than, so we've got white spaces in all of these locations, we can say that this is not a 7. And we are right in 48,000 cases, and we are wrong in about 900 cases. So 900 of those images actually are 7s, even though they comply with these decision rules. So the training, the tree is not perfect. It makes about 3% of a training error. And when we are looking at the test error is very good. So it's just about the same as the training error. So very similar. This tree is not overfitting. And so this is a pretty good tree. We can compare the performance of this tree with the logistic regression and the random forest using a random, using an ROC curve. And so here's the ROC curve for the tree. It's that green line. And you can see that initially the tree is going up higher and quicker than the logistic regression. So for very small false positive rates, the tree is the model that performs better than the logistic regression. And then the orange line crosses over the green curve and becomes the better model. So overall, the logistic regression is better than the tree. But initially, the tree shows a better performance. So for small false positive rates, the tree is the better model. So sometimes so not only do we look at the ROC curve and the area under the curve, sometimes it also depends on which error is worse than the other error. So if the false positive rate, so if it's very important for us to not come up with false positives, so accuse an image of being a 7, even though it's not. If we want to have a small false positive rate, we should use the tree over the logistic regression, because in order to get a small false positive rate, the tree shows better performance than the logistic regression. Overall, both logistic regression and the tree are massively dominated by the random forest. So the random forest is just the baseline in the background to how good can we be with just something that's run out of the box. Okay, so let's have a look at this out of the box running model. So what the idea behind a random forest is that one tree is just not good enough sometimes. So what we do is we fit multiple trees instead. Then in order to evaluate a new observation, we run the new observation through all of these trees that we fit. We come up with predictions from each of the trees, and then we use a majority vote on those results to say what an observation is finally going to get. So here we've got trees that are trying to determine whether somebody is healthy or not. So we've got healthy and diseased. And this is a terrible example, but I hope it's bringing the point across. So we're looking at age, old and young, as opposed to male and female, as opposed to whether a person is tall or short. And we've got these 3 trees. So now we've got a new sample of an old retired male who's short. When we run this through this new observation through the tree, we come up with tree 1, giving us back this person is more likely to be diseased. Tree 2 says this is a perfectly healthy individual. Tree 3 is going with diseased again. So in order, using a majority rule, we would say, well, diseased it is. But we can also put a probability on that. So we can actually keep track of how often a tree votes for one thing over another, over the other class labels. So here we would be able to say, well, the score from the random forest is really 2/3 for diseased. And if the score is really close to 0.5, we already know, yes, the random forest might have a small majority for one class over the other, but that might not mean as much to us as a score that is unanimous. So where all trees say this is one class and not the other. So obviously there is some weight in how many trees vote one way over the other. Okay, so multiple models. So how do we now create different trees based on the same data? Essentially, that happens by mixing things up. And we can mix things up by randomizing. So rather than using the same data to grow a tree, what we do is we only use a subsample of the data. So what we do is we pull data with replacement. So we might sometimes end up using the same observation twice in our sample. So we sample the data, and then we select additionally in each node, we only select a subset of features. So we're just taking, let's say, 20 features rather than all 784 features. And we just use the best out of those 20 features to grow a tree. So you can imagine that these trees are not the huge, nice looking Douglas firs of very strong, great looking trees. They are more the high altitude little pines kind of trees that are a bit crippled. We're crippling them because we're not using all of the data and we're not using all of the features. What we gain from it is we get a lot of these kind of imperfect trees, and we put them all together, and they are stronger together than a single perfect individual tree. So by doing this bootstrapping, so sampling from the data, when we sample with replacement, on average, we leave out about 36% of the items from a data set. So 36% are not included in the fitting of each individual tree, which means that we can use those holdouts, those 36% of observations that weren't used in fitting a tree, we can use those to evaluate just each individual tree as it's grown. So we have a separate training test situation for each individual tree. So we can use those emitted values to estimate the error that we see, and that is what's called out-of-bag error. So inside the bag is the subsample of the data that we've used to fit one tree. The out-of-bag sample is what wasn't randomly pulled to fit that individual tree. So how does that look like? With the random forest that we use to determine whether something is a 7 or not, we're just using 50 trees. And here I'm plotting on the right-hand side, you've got the number, or on the horizontal, you've got the number of trees. On the y-axis, I'm plotting the out-of-bag error rate. So you see 3 lines here. We've got this green dotted line, a black line, and then a red hatched line. So the green line corresponds to, that's the error rate for the things that we call not a 7 that are actually a 7. So those are the 7s that we miss. In red, those are all of the images that we don't call a 7 that actually are a 7. So that error rate is much, much smaller. And the black line in the middle is the average between those 2 lines. The reason why this is not, this black line isn't perfectly between the green line and the red line is because the green line is based on just 6,000 or so, a little bit more than 6,000 images that are 7s, whereas the red line is based on the 53,000 other images that are not 7s. So we've got a huge imbalance in our tree or in our random forest. So that's one thing that we might want to address in order to improve this particular random forest or a tree for this situation, because we do have an imbalance in our classes. Okay, and I'm seeing that that there's questions in the Q&A. Anthony, would you mind reading those questions to me? I don't have control over the mouse.
Sure.
Thank you.
So the first one from Jenny is, in developing the training set, how do you provide for original writing as opposed to copied writing?
Okay, I'm not completely clear about what do you mean by original writing as opposed to copywriting. Okay, I believe that it refers to training data. But I think okay, so I think I'm seeing where that question comes from. So when we're dealing with any kind of same source, different source problem, we are almost always in the situation that we have very, very few same source comparisons and hundreds and thousands of different source comparisons, because whenever somebody's writing something, we automatically can compare that particular writer to all of these other writers that we've got. but we have to force that writer and do another writing for us in order to get a same source comparison. So that is absolutely a problem. And one of our projects at CSAFE is trying to address this imbalance and also break some dependencies between different kinds of comparisons along the way. So Danica Omen is working on that particular problem. So I can reach out to her and see what kind of suggestions she can provide us with, besides using all of the same source comparisons that we can possibly get and just sample from the different source comparisons. That would be my approach to that situation.
So Jenny has, excuse me, another question as well. And just to make sure that we answered that, or address the question correctly, the way that it was asked, I'm going to allow Jenny to speak.
Okay.
So Jenny, you
Hi,
should
Jenny.
be able to.
Thank you for your question.
Good evening. How are you?
Pretty good.
Thank you very much. Yeah, I understand the answer to my first question. In practice, we deal a lot with what we call collected specimen writing.
Yes.
So yes, in that instance, you would be dealing with documents that contain wet ink writing. So that's original writing. So I can see the problem. On my second question, I said that so far it appears that picture impressions used to identify, for example, a 7. That's the examples you've been describing. Now, I understand it that the logarithm is then asked whether it looks similar or not. And that is how you identify your 7s. But what we are interested in as forensic document examiners is the individualization.
Yes.
So it goes to who wrote it. I know it's a very difficult question, but I would just like to get your idea and your train of thought, where you aiming with this.
Yes. So in that sense, the MNIST database is still a toy example, even though we are already dealing with 60,000 images. It's just looking at recognizing, hey, this is a 7, and not this is a 7 by the same writer, and this is a 7 from a different writer.
Yeah.
I absolutely see that. We can use the same kind of tools to, so the same kind of feature extraction for same writer, to answer the specific source question of whether this writing was done by this person. But we need a lot more than just using
You see, the problem is
from that image. Yes.
Yeah, all data like fingerprints, if you take that is stable data. So it's always the same. Handwriting presents a special problem because the data that you get from handwriting is not stable in nature. So
yes, it's not that stable. Yes, I absolutely agree.
And I think if we can breach that issue of the unstableness of handwriting and signature data, I think that we will be far down the road there.
I absolutely agree. Yes. So in that sense, we're still dealing with toy examples before we can actually look at handwriting data.
Yeah, but that would impact on how you develop your trees, if I understand it correctly.
Yes. Yeah.
Okay, thank you.
So yeah. Great question.
Right,
thank you.
Thank you very much. I appreciate it. I'll mute now.
Yeah.
Excellent. And we have one more question, and this one is from MK, and it says, so are the out-of-bag items a sort of validation set?
That's a good question. Yeah, I think we could call it a validation set. So it's a holdout from the training, but it's not a holdout for everything. So it's not a holdout for all trees. yes, that is, yes, right idea. So it's a kind of a validation set. Usually people don't refer to the out of bag samples as validation data, but yes, that's a good point. Okay, so with the random forest, we can see as we successively increase the number of trees that we include in our model, the error rates go down. And you can see that initially the error rates go down a lot faster. And then the errors level out. So that's where we can say that it doesn't really help to include a lot more trees because the error rate is not going to keep going down infinitely. It will just level out. So there we can only get down to a level, and that level usually depends on each problem in itself. So each problem will have a different kind of error rate when we're just using the same model with the random forest and we don't include additional features in the data. For example, so let's have a look back at the advantages of trees. And I've just switched out advantages of trees, substituted it with random forests if it's this, if a particular advantage is still valid. So random forests can absolutely deal with large data. We can include multi-class classifiers. Initially, we said trees are easy to interpret. Random forests, unfortunately, lose that. I'm pretty sure that one tree is relatively easy to explain to somebody. Having 50 or 500 or 2,000 trees to explain to somebody, that is a loss in explainability. So we unfortunately lose that. Random forests still can deal with numeric and categorical variables, and nonlinear relationships don't negatively affect random forests. So on the advantage side, we lose one advantage of trees when we're switching to random forests, so a multitude of trees. On the disadvantage side, we get rid of two big disadvantages, maybe even three. Two big disadvantages for sure. Random forests are a lot more stable than trees. So that's a tree is an individual. A random forest is an average. So that's where statistically the central limit theorem kicks in. So we're averaging across a larger number of tree results. That automatically means that the more trees we include, the more stable our results are going to be. So even if we don't reduce the actual error anymore, we're a lot more certain in our answer when we're including more trees. So small changes in the data is not going to affect a random forest that much, because by default, each tree in a random forest only uses about 2/3 of the data anyway. So it's not going to matter unless we shake up the data completely. Trees overfit easily. Random forests don't, because we're making the individual trees so bad that we really don't overfit anymore. We're just fitting special cases, and we're averaging across those special cases. So we're getting rid of two disadvantages that we see in trees. So essentially the advantage of random forests over trees is that random forests address the instability of trees and get rid of overfitting issues. but we lose the interpretability at the same time. So what we do instead of sometimes using random forests for the final model, we often use random forests to measure, to just get an idea of which of our features are actually important. So we're getting back to the idea of Genie impurity. So when we're building trees, each tree looks at each variable and the amount of the maximum amount that each variable can reduce the Genie impurity. And the tree just keeps track of that. Now the random forest has a multitude of trees. Each tree tracks the feature importance of each variable. So that means that we can come up with an overall feature importance for each of the variables that are involved. So here we're looking at the, how many were there? 784 features that make up each one of the images from the MNIST data. And you can see how each one scores. So here we're just looking at the top 20 features or so. We're looking at the mean decrease in the Genie impurity. And you can see that variable 743 shows a huge reduction of the decrease in Genie impurity, followed by 406, followed by 378, and so on. So when I ran the logistic regression initially, I told you that I magically came up with some variables that seemed good. So that's exactly how we identified these variables, by running a random forest, pulling out important variables, then using those, this manageable subset of important features and including them in a model that is easily explainable, easily interpretable, just not as good overall. So we can use the or misuse the random forest that way. And it will give us a good way of finding important features this way. So random forests, what we can do in practice is to use random forests as a tool to create a baseline model of how good we can get if we just use this rather complicated tool of random forests, and then measure our performance of other models compared to this random forest model. And we can also use the random forest to extract important features and then put them into the more explainable or interpretable models. So let's see that in action. So I want to go into bullets. I would love to have a handwriting comparison. I will ask my colleagues and see whether they can explain handwriting to me in the next week. We'll see how that goes. So machine learning in action, comparing of bullet striation marks. And that is all based on 3D topographic scans. So 3D topographic scans is what's being used in comparison in confocal light microscopes. So essentially confocal light microscopes work just like LiDAR. So we can use LiDAR from helicopters to measure huge topographic surfaces. So this is, just to bring Iowa in for a little bit, this is the Effigy Mounds National Monument. When I dragged my kids over the monument, they were really disappointed because it's hard to see the marching bears. It's just overgrown. It's much better to look at from this particular viewpoint. And similarly, on the right-hand side, we've got an image of a bullet in a stage with our confocal light microscope. So what we're capturing is this little green spot on the bullet at the base of the bullet. And that looks in a rendering a bit like that. So we can see the striation marks in the middle, and then grooves on either side, on either side of that land engraved area, and a bit of break off of the bullet along the bottom of the bullet. Okay, so here's just a zoom in, and you can see the pixels here. So this is not a photograph. This is a pixel rendering. We've got 2 Sensophore confocal light microscopes, and I don't want to make this an endorsement. I'm just reporting what we're using here. We've got multiple undergraduates who are doing nothing for us but scanning images for 10 to 15 hours a week. And we get 3D topographic images that show height measurements on a regular XY grid. The grid measures that we're using here is 0.645 microns. So we've got each pixel represents 0.645 by 0.645 microns. And the total area that we capture for each land is about just over 2 millimeters width, so just under 1/10 of an inch to about half a millimeter height, so 0.6 millimeters. Similarly, we've got cadre top match for cartridge cases, but I really want to focus on just comparing bullet striations. So here we've got, and this is what the data looks like. We've got X values, we've got Y values. X and Y are on a regular grid, and then we've got Z values that show us some height measurements. In microns, we're using X3P standard. The X3P is an ISO standard, and it's been adopted by the Open FMC, the Forensic Metrology Consortium. This link gives you a little bit more information about the consortium. So X3P files, the idea is that when we're working in these X3P file formats, we can include meta information about how a scan was acquired. We can include some instrumental information. We can also include information about what area of a bullet or cartridge case was captured, what kind of material we see, observe in the cartridge case or bullet. And then additionally, obviously, we've got this matrix of numbers. The reason why we use X3P files is they're exchangeable between different systems. So you can imagine that one lab acquires the scan and another lab acquires a scan for material from another scene. And then labs can exchange these files for just a quick comparison. And in case this quick comparison shows a potential interest, then the labs can actually exchange the physical specimen. So that's why we need to push for that ISO standard rather than having proprietary file formats. So X3P is an open format and can be read by software that's other than the vendor software. Usually, X3P is not the native format that a vendor is operating in, which means it's a little bit tricky to get to, but usually you will be able to see that as file export as from the software that comes with a microscope or a capturing instrument. And usually there's a way to get X3P out. You can look at X3P files. There is a Chrome extension. So if you're allowed to use the Chrome browser, you can download this Chrome extension. That will mean that you can just take an X3P file, plop it into your browser, and it will open as the image, as the scan that, and you can even rotate the scan. So it's pretty cool. Have a look at that Fix3P file extension. It also allows you to look into the additional meta information that is that's available, that's coming along with the file. So let's assume that we have dealt with all of these X3P issues and we actually have a file. So here, this is a file rendering. So what we want to do on the statistical side now is, rather than taking this whole scan and comparing that whole scan to another whole scan, like we were doing for the images of the digits, what that comparison is would be doing is, yeah, I'm pretty sure this is a bullet. It's shaped like a bullet. It has grooves. It looks like a land engraved area maybe. So that's not something that's particularly suitable for us for a comparison. Rather, what we want to figure out is whether two separate scans that come from two separate bullets, whether those two bullets likely were fired from the same barrel. So that's the question that we want to answer. That's the common source question. So what we need to do is we need to try to work with the data in a bit more statistical way. And extract features from something that will actually capture the individuality of a particular specimen. So for that, we first need to identify a region that's suitable for matching. You can see that there are stria in the sort of bottom half of that land engraved area. So here we are just looking at a red area. We could probably increase that area and make this a bigger line. But in this area, we will find some striations. So we pick this region close to the bottom of the bullet. We try to avoid the break off. We also try to avoid an area where there's too many missing values. So you can see that we're only capturing the groove on the left-hand side just a little bit. So we could actually shift this area up a little bit to also capture a better area where there's no missing values just before we go into the groove. But this area will work. So what we do then is we sort of turn this bullet area around. We just use the area under that red. We just use the values under the red area and we average across those. So that's the difference between the image with the spikes in the back and the smoother image of the dots in the foreground or in the bottom picture there. And you can see on the x-axis, we just have values from 0 to about 2,500 or so. That's a location along the x-axis. It doesn't, we can shift this left and right. So the 0 isn't fixed. It's a relative measure. X is measured in microns. So we've got about 2,500 microns from the left-hand side to the right-hand side. And on the y-axis, we have also microns. So we see the curvature of the bullet. We see the grooves, the shoulders that go into the groove areas on the left-hand side and the right-hand side. And you can see that overall we have values from about 80 microns to 200 microns. And again, the absolute values on the height axis are don't have any meaning. Those are just relative extensions. So we might as well shift it into 0 to 40. Oh no, 0 to 120. That's just because I can't calculate. So we've got about 120 microns in height differences from the highest surface area to the lowest area, which is just before the groove start. So what we do next is we want to capture the smooth, that curvature. And the grooves are making that a little bit tricky. So as a first step, we identify the shoulder locations by just finding a minimum in these curves, taking those values and then removing everything that's outside of those areas. Now we just have the land engraved area. So we just snipped off all of the groove areas. And what we do now is we take the curvature of the bullet curvature using, it doesn't really matter how, but here we're using a non-parametric smooth. The advantage of that, instead of just trying to fit a circle because it's essentially a bullet, is that sometimes bullets might be damaged. So they might no longer be a smooth round surface, but they might be just bent a bit. So the non-parametric smooth can accommodate for that. So we have the smooth, and what we're really interested in is the little things that peek out from the smooth. So in order to get to those little things that peek out, we're taking the residuals. So you can, now we actually have the black line. So the black line at the top is sort of the same as the black line along the bottom. And you can see how the signature has a very different height extension. So the signature is in the range of maybe plus minus 4 microns, whereas the relative height along the top has this 120 microns. So essentially what we're doing is we're just looking at how far away each one of those peaks and valleys goes away from that blue line. So that's our signature. And then we're starting to compare signatures. So here's a second signature. And you can see that these two signatures are not identical, but they look very similar. So those two signatures are actually from two different bullets, but those two bullets were fired from the same barrel. So what we want now is we want to compare these two signatures and see how similar they are, and also how different they are. So we want to quantify the similarity. So here we're shifting the signatures left and right to find the perfect alignment, or best, I shouldn't say perfect, nothing is perfect. So we want to find a good alignment between the two signatures. And now you can see that, so one signature is hatched, the other one is the drawn through line. And you can see that they are indeed very similar. There's some peaks that are a little bit higher on one signature, some peaks that are a little bit better expressed in one signature over the other signature. But overall, these two signatures look very, very similar. So the idea is now that we use these signatures rather than the original scans as a way to identify features that we use in order to distinguish between two signatures that come from lands from the same place or from the same barrel, from the same source. And so those features are supposed to help us distinguish between same source and different source. So rather than, so what we can do in this is we can compare where striations are and then see how many of these peaks and valleys match up with each other. We can count the number of matches and mismatches of peaks and valleys. We can count consecutive matches. So that's similar to Biasotti's idea of the CMS. So how many consecutive matches do we count? And on the other side, we can also count how many peaks in a row don't match up. So CMS and CNMS. So consecutive non-matching stria. We can have a look at how deep peaks and how high valleys are. If these are very strongly pronounced, so that means that a bullet or a barrel is good at marking the bullet. So we're a lot more confident if we have really strongly expressed stria that match, as opposed to flat scratches all over, but that don't, that are not as well expressed, but they might match. So the depth is important. Then we can also have a look at and calculate the area between the signature, and one measure that statisticians love to use, that I love to use, is the cross-correlation function, which is calculating, giving us a number between -1 and 1 for how much do these signatures move in sync. So if there's a peak in one, is there a peak in the other? If there's a valley in one, is there a valley in the other? So they don't necessarily need to go all the way down into the same. So that the height doesn't need to be the same. But as long as they move in the same way together, the cross correlation is going to be high. Okay, so we've got these features, and we can, so similar to what we did with the Swiss banknotes, we can now use these features on a training set. And here we're using HAMB 252 as a training set, and distinguish between known matches and known non-matches. So we've got a lot more known non-matches compared to the known matches. So we do have that imbalance there, but I still want to use all of the data. And what you can see here is that cross-correlation function at the very end divides the best between known non-matches and known matches. But you can also see that among the known matches, so that light blue curve, there's quite a few cases where things that we know are known matches just don't look like known matches. They just look quite different, and they, in terms of the values that we see in terms of cross correlation and pretty much all of the other values, there are some that just don't look like matches. So in terms of their measurements, we don't see that they are more similar to known non-matches than known matches. So we see that second mode for the number of matches. We see that second mode for the number of non-matches. So oftentimes we're dealing with the situation that something that we know to be a non-match just doesn't look like a match, but looks a lot more like a non-match. So we've got these features, individual features. We can put that into a tree, and this tree should now look familiar. So what we see is that number of matches and CCF look very similar, are being used, are very important. And we see that, so this tree is actually quite a good tree, but because of the instability of trees, so that's the main reason why I don't want you to just take this tree and apply it to actual casework. This is just a single tree, and we don't know how this tree is really going to work when we have data that's very different from what it's being trained on. So here we've got a decision tree, and it's not bad, but we can use a random forest that uses all of these features. And this is the result from a random forest. So for this we trained this random forest on 2,000 trees. So we've got 2,000 trees using the 9 features that we talked about, these ones. So we put all of these in. So 2, 4, 5, 6. Oh, it's just 4. Can't count. It looks like 7. So 7 features. So these 7 features go into this particular random forest. We're using Hamby. So be aware our training data only covers 10 barrels. So it covers 10 barrels and 35 bullets from these 10 barrels. So it's just one set of the Hamby study, Hamby 252. And we get these random forest scores out. So you can see that we're mitigating the the same source is usually very high. So most of the curve is above 0.5. Different source is shown in gray. Most of the different source random forest scores are between 0.25 and 0.5. But there is some overlap between the random forest score of different source and same source. But this random forest model is operating on land-to-land comparisons. So what we can do in order to make this better and come out with a bullet-to-bullet score is we can average across all 6 lands. That will actually get you to a much better separation between known matches or same source and different source comparisons. And I don't want to go into that too much. So we'll start back up here, and I'll just go and take questions now. I hope you don't mind. We have a random forest model that shows us really nice separation of the random forest score. in order to, what I want to take out. So I'm ending on the same note as last time. How reliable are the results? In order to, so both trees and random forests and logistic regressions are going to give us an answer when we have a new observation. And the answer is going to tell us, or trying to tell us, whether something is same source or different source. What we don't know is how reliable these results are. So it's really crucial to keep in mind what data was used to train any model on. And that's helping us to assess the reliability, or rather hinder us at using these models in every situation. So for the random forest, for striation marks on bullets, we need to ask a question whether the data is representative of the general population. And the general population would be the combinations of ammunition and firearm. So ammunition is important because different ammunition has different surfaces. So some surfaces mark better than other surfaces. Some firearms are going to mark better than other firearms if the rifling is different, like in a clock. The stria are much harder to find, if at all, and we don't have nicely set lands. So can we use a random forest that's trained on 10 barrels of Ruger P85s? Can we really assume that this is representative of the general population? No. So that means that all of these algorithms and models should only be used within their limitations. And the algorithms and models should also always state what data they were trained on, and address any kind of limitations, so that we're not accidentally using or misusing models that outside the scope for what they were meant for. Okay, so rant end. We have another couple minutes, so I'd be happy to take questions. I'm getting out of presentation mode, and that means I can answer question now. So first question, I was wondering if there is a third signature. Can we tell whether the timing of the bullet fired? Can we tell anything from when of how the signature changes over time? So one of the okay, so when firearms examiners are looking at firearms and make comparisons to bullets, usually the assumption is that the firearm wasn't used very heavily between when the evidence was collected and when the firearm was confiscated, collected. So if there's really a lot of shooting going on between bullets, we might not be able to make comparisons back to the firearm or identifications back to the firearm. There are a couple of studies that look at the persistence of particular barrels and look at the stability of stria marks over time, but I haven't seen any papers that would look at or allow us to answer the question that you would like to answer when a bullet was fired, whether it was before or after a particular other, when another bullet was fired. So I don't I don't know of any model that could do that. Okay, so it is evident that to move from identification to individualization, every model needs to be customized to fit the application. I absolutely agree. So the idea here of this workshop is not really to give the best case scenario for a particular application in a particular area. Rather, I want to explain the statistics or the ongoings of the algorithm behind first. And it's always the difference between Stat 101 and actual answering questions with data in a high stakes setting. The 101 questions tend to be really simple and very concise. Similarly, the models that we're using here are based on almost toy examples. Maybe not so much the last example, but definitely the MNIST database, even though we've got 60,000 images, which sounds like a lot of information. Those are just little images where we want to say, well, this is a 6, and I recognize a 6 when I see a 6. And we just want to get the algorithm to get to the point that it recognizes a 6 as opposed to a 9, and just assume that algorithms inherently are very, very stupid. So the idea of artificial intelligence or statistical learning is very similar to teaching. I don't want to bring our kids here into this discussion, but it's similar to teaching somebody to recognize and to tell the difference between, I don't know, a pen and a spoon. Both look very similar from the side, but when we turn them, we can definitely tell them apart. And similarly, a simple model is going to say, wow, I recognize this as a spoon. And it might not have perfect recognition as a spoon, but it might not recognize your spoon. So yes, individualization is a lot more tricky than just identification. Thank you so much. Thank you for coming back to part 2. I'm looking forward to part 3. If you have any particular wishes, please let Anthony know. I'm sure that he's going to send out the survey in just a little bit. So if you have questions that you would like to be addressed next time, put those in and I'll see what I can do. I'll try to also find a good handwriting example and see what we can do with a random forest. But generally, I want to talk about neural networks. And at least that's on the plan for next week. Thank you so much.
Dr. Hoffman, thank you so much for your time again and for sharing this with us. Thank you all for joining us. We hope you have a great day.